of CuTe layout algebra and its category-theoretic interpretations. So the main speaker is going to be Jack Carlisle, who's a research scientist at Colfax. Jay Colfax is also here, who will mostly be giving like some of his comments and thoughts. Chris is going to be from NVIDIA, is going to be co-hosting with me, and he's been like one of the main people also behind like CuTe layouts at NVIDIA. I think like for what it's worth, like the talk will be like on the longer side. I think we're sort of expecting like a 2-hour talk, but Jack has promised us to make this like an accessible talk where you'll have like many entry points. So please, Jack, without further ado, take it from here.
Wonderful. Thank you. Yeah. So first of all, I'd just like to thank the organizers and the hosts for inviting us to give this talk today. I've been looking forward to this. The work that I'll be presenting today is coming from the Colfax research team, especially from myself, Jay, Ruben, and Paul, who are listed on the screen here. As was already mentioned, we're fortunate to have Chris as a guest host. And so I'm hoping we can have a very informative discussion of all of this stuff. I'll leave it to the moderators to specify the manner in which questions are asked and answered, but I invite any and all questions. So right, let's get started. So let's start by just giving sort of a brief overview of what we're going to talk about. Let's make sure we can get this to work. So the talk is sort of naturally split into 2 parts. So the first part is going to be purely expository. So this will be these first 2 sections. And in these sections, we're going to talk about CuTe layouts and the important operations that they support. So if you've worked with CuTe before, you'll be familiar with things like, or at least you've seen things like logical division, logical product, composition, variants of these things like zip to divide and things like this. So we want to give some sort of general introduction to these concepts. And then the second part of the talk, which will consist of these 3 sections, is going to be our original work, where we sort of the goal is to connect this beautiful and novel sort of idea of CuTe layouts from computer science to some well-established concepts from mathematics and abstract algebra, such as categories and operads. Maybe some of you know lots about categories and think categorically regularly. Maybe some of you have never seen these things before at all. I think the point is to express these ideas in an accessible way. So I encourage you to follow along, and we'll be able to use some cool, fancy mathematical language, but it should be accessible to anyone with an interest in this general sort of GPU programming stuff. So without further ado, let's go ahead and get started. So let's set the context, right? In the world of this GPU programming and related things, we might care about something like a gem kernel, which is going to compute the matrix product C of some matrices A and B. And so maybe our operand matrix A has size M by K, and maybe our operand matrix B has size K by N. So in this case, we'd say that K is the contracting dimension of this gem. Then the output matrix C is going to have shape M by N. So the point is that these operands, as well as the output of this kernel, are tensors, right? Tensors are some sort of generalization of vectors and matrices to arbitrary dimension. So here, these first 3 guys that we encountered were matrices, but it's common to encounter tensors of higher rank too. Like, for example, if you've worked with attention-like kernels, you might have seen some tensors Q, K, and V with a shape that looks like this. So these are rank 4 tensors, which have not only, or they're not M by N in any sense, right? They have a batch dimension, they have some sequence length, they have some num heads dimension, and they have some fixed head dimension. And so we have to deal with things that are higher than 2-dimensional regularly in this sort of business. So let's talk about how tensors are encoded in CuTe. So the point is that in CuTe, a tensor is specified by 2 pieces of data, specified by an iterator and a layout. The second piece, the layout, is what we're going to focus on today. So a layout, like this one L we've written here, consists of 2 pieces of data, right? It has a shape, which we denote S, and it has a stride, which we denote D. And this layout is going to tell us, so the idea is right, if we have some CuTe tensor, then this iterator is going to point to, say, the 0th element of the tensor. And if we want to access the other elements of the tensor, we're going to use this layout to offset the iterator, and then we can dereference to access whatever the value is. So let's look at some examples of layouts. Here are some typical examples, right? This guy is a 4x6 matrix, corresponds to a 4x6 matrix. We'll see later on that this happens to be what's called a row major layout. But you can see some more exotic examples too, right? So maybe I'll just let this lie, and we'll take a look at some images which depict these layouts. But one thing I want to emphasize is this, right? In our first 3 examples that are listed here, the shape and the stride are both tuples of integers. But that's not always the case for a layout. Layouts can have shapes and strides which are nested tuples of integers, meaning each entry may be an integer or a tuple of integers or a tuple of such things, etc. And so we have to grapple with this sort of nested structure. So let's take a closer look at some of these examples. So here on this next slide, we have 2 great examples of layouts. This one on the left is a layout of shape 4x6. And this is what's commonly called the row major layout. Why is this called row major? Well, the idea is that this is sort of describing how the values of our matrix are laid out in memory. In the row major layout, the values in a given row are contiguous. Whereas if we look at the values in a column, these guys are strided, right? Here we're offsetting by 6 whenever we change the row index by just 1. On the other hand, we have the cousin or sister or brother of this thing, which is the column major layout. So again, this is called column major because if we look at the columns, we see each column is contiguous in memory, whereas each of the rows is strided, right? And so maybe we should just briefly connect this to the notation of the layout, right? We can see here that like 4x6 is representing that we are looking at a 4x6 array of values. And then this 6 and 1 are telling us how we increment the values contained in each of the cells in this image, right? So here the 1 stride is corresponding to +1 in this direction, and the 6 stride is corresponding to +6 in the downward direction. Similarly here on the right-hand side, we have +4 going along the rows and +1 going along the columns. So these are maybe the most common layouts that one will encounter, but they're not the only layouts that one will encounter, and they're certainly not the only layouts that one will need. So let's take a look at some more exotic examples. So let's start with the example on the left-hand side. This is something that we might call a broadcast layout. I'll say broadcast or perhaps broadcasted. But in any case, we can see that the values in these cells are not unique. Some of them are repeated. More precisely, this is a layout which might be used to take a vector of length 4 and broadcast it into a matrix of size 4x6. So let me write this down. Here we might have a vector of shape 4. And we might want to broadcast to a matrix of shape 4x6. This is a very important operation. For example, one might care about something like a block scaling operation, like doing a block scale gem or something like this. In this case, you look at chunks of, say, 16 or 32 consecutive elements in a matrix, and you want to assign a single scale factor to each length 16 chunk. Well, you can store the data of that scale factor matrix more compactly by just broadcasting along these chunks of length 16 or length 32, rather than storing redundant copies of the same data. Let's take a look at one more interesting example here, which is what we might call something like a strided layout. This is informal terminology that I'm using here. But the point is just that for this layout, right, it kind of looks like the row major layout because we're contiguous in the row dimension, or we're contiguous moving along a row. But we see here that we don't have the expected stride, right? Here, if we travel along the initial row, we go 0, 1, 2, 3, 4, 5, and then we skip 6, right? We go all the way to 12. And so the idea is that these are layouts which might arise whenever we slice into a tensor. You might imagine that this is sort of the left half of a 4x12 matrix that we split into two. And so these strided layouts are going to arise naturally when we do something like tiling an operand or tiling a tensor. We'll see more examples of this later. And now I want to look at one final example of this form, right? And this is maybe my favorite example. This is what we might call an interleaved layout. And so let's spend a second understanding this big diagram, right? It takes a minute to parse. If we look down at the bottom at the expression of the layout as a pair of a shape and a stride, we'll see that, move this guy out of the way, we'll see that this thing has sort of logical shape 4x6. But the idea is that this layout is such that neither the rows nor the columns are contiguous in memory. Instead, what we see...
Sorry, Jack, you mean 6x8 here?
6x8, of course. 2 times 3 is 6. 4 times 2 is 8. Instead, what we'll see is that each one of these 2x4 tiles is itself contiguous in memory. So let's write this down. That's the key point of these guys, or a key point. Each 2x4 tile is contiguous in memory. That's if the layout of a tensor is this layout, right? These interleaved layouts are also used for other purposes. Maybe before we take a look at that, let me also connect this stride nested tuple we see down here to the image above, right? So if we look at this 6 shape, this 2, 3, we see 2 strides, 4 and 16. So the 4 corresponds to this jump here, and the 16 corresponds to this jump here. Similarly, the 1 and the 8 correspond to the +1 offset here and the +8 offset here. Again, later in the on in the talk, we'll develop maybe a stronger vocabulary for describing things like this. Okay, great. So far we've been discussing layouts and describing them, or we've motivated layouts because they are used to describe and specify how some sort of logical matrix or tensor is laid out in memory. There's also another important use of layouts, which is to partition data among agents. So you might want to partition a matrix among clusters of CTAs or among CTAs or among threads. And one instance of this sort of thing is a thread value layout. So I want to look at 2 examples of these next. So here we're looking at an image pulled from the PTX documentation of the accumulator layout for a certain MMA sync instruction. The point is just that whenever you use this MMA sync instruction, the output, which is some, I guess in this case, 16x8 matrix of values, is partitioned among threads. In this case, it is partitioned among a warp of threads. And so whenever you want to write this data out, for example, you need to understand what the thread ownership pattern is so that you can correctly copy data or manipulate it or do whatever else you might want to do. And so in this case, our thread value layout is described as on the top of the screen. So here the 4 times 8 is telling us we have 4 times 8 equals 32 threads. In other words, 1 warp. And then here, this 2 times 2 is telling you that each thread owns 4 values. This thread value layout will allow us to take our thread index and slice into this layout to obtain the correct sort of fragment of the accumulator that's owned by each thread. So we can look at a bigger example of this sort of thing too, right? Maybe we won't dive into it too much, but here's an example of the accumulator for a WGMMA instruction. And so maybe for the formula that I wrote at the top of the slide, we're imagining here that n is equal to 64. And so this is showing a 64x64 accumulator tile. This is something which is held across a warp group. In other words, 4 warps or 128 threads. And you can see that the layout is, well, a little bit complicated. I mean, you have to zoom in a little bit to parse it. But the idea is that, okay, well, we have 4 warps, or rather, I should say, truthfully, 128 threads. And each thread is going to own a tensor of shape 2 by 2 by 8. And so, for example, if we want to understand which values are owned by thread 0, well, that should look like this pair of values here in the top left corner, as well as some others. It's going to own 2 out of every 8 consecutive elements in the 0th row, as well as 2 out of every 8 consecutive elements in the 8th row. And this pattern is sort of tiled across the accumulator. In particular, this first collection of 16 rows is owned by the initial warp group, or the initial warp rather. This is owned by warp 1, warp 2, and warp 3. So we can see that if we want to use these important hardware instructions, we need to understand how this partitioning of data among threads works. And CuTe layouts are a very powerful tool for doing this thing.
And even so, Jack will get into this soon, but it's worth pointing out that the mapping this layout represents is the thread value to 2D coordinate mapping, the thread value to MN coordinate mapping. However, the strides here are apparently integers and not 2D coordinates. So there's implicit remapping of the one-dimensional integer to a 2D coordinate. This is called the colexicographic isomorphism, and Jack will be discussing this momentarily.
Yeah, thank you, Jay. Okay, great. So let's continue on. So the thing I want to mention next is that one cannot take, for instance, a 2D array and label it by arbitrary integers and expect that to correspond to one of these CuTe layouts. And a very simple and probably minimal example would be this guy right here. Here we see that the labels are 0, 1, 3, and 2. Okay, and why is that a problem? Well, the shape is certainly 2, 2, right? And if we need to assign a stride to this, well, this stride certainly has to be 1, okay? And then this stride certainly has to be 3, okay? Or in fact, rather, this is reverse. This should be 3 and 1. But then if that were truly the case, we would expect this to be equal to, well, 3 plus 1, which is 4, which it's not. And so this is an example of a very simple pattern, which is not represented directly by a CuTe layout. However, CuTe supports extensions of these layouts. Like, for instance, for this layout, we could express this thing if we composed our layout with what's called a swizzle function. And so this brings up the notion of a composed layout, which is supported in CuTe.
You know the other way to do this, right, Jack?
Please do share. What's the other way to do this?
So in the CuTe paper, I try to focus on abstracting the strides of these layouts. And so rather than having integer strides inside of these layouts, you can actually abstract the strides to represent swizzle layouts of this form. And swizzle layouts of this form can be represented by layouts with so-called F2 strides, where addition is replaced by an XOR operation. And then you can construct strides such that when you add them together, they XOR in such a way to create these, to create the appropriate offsets that you're showing here.
I see. Okay, very interesting. So yeah, so it sounds like this is an instance of using, I mean, when I hear XOR, I think of like F2 linear addition, right? So this is some sort of F2 linear algebraic structure that you've included here. Yeah, very interesting. And I think maybe now would be a very appropriate time to promote or advertise that Chris has posted his paper, which is titled CuTe Layout Representations in Algebra. We'll have a link at the end of the talk, which contains a lot of wonderful expository stuff, as well as fascinating new and original research. And so everyone should definitely take a look at that. Additionally, I'll also advertise that we have our Colfax research has our own paper, which discusses a lot of like some of this expository stuff, as well as a lot of the more original work in the latter half of the talk. We also made a blog post where you can read a more narrative form of this information. So in any case, at the end of the talk, we'll advertise a bunch of places where you can go to learn more about these sort of concepts.
Yeah, let me just say that we'll be addressing the notion of having strides valued in a more general object, such as a module over the integers, in the end of the talk.
Yeah.
So there's a sense in which the theory we discuss can be extended as well to cover such cases. And is actually a somewhat, I think, a slightly interesting extension. So yeah, we'll be discussing this at the end of the talk.
And to answer the question in chat, yeah, there are within the CuTe paper, there's currently on archive right now, there are a lot of examples of CuTe layouts with F2 strides, as well as coordinate strides, as well as integer strides. And there's a couple of other interesting options.
So in this talk, for the vast majority of it, until the end, as I said, we'll be discussing CuTe layouts with integer strides.
Wonderful. All right. Any further questions or comments before we continue on?
We can keep going.
Wonderful. Okay, great. So we might ask, in what sense precisely do these images that we've looking at represent the layout by which they are labeled? And so at this point in time, we need to specify some notations so that we can express these things a little bit more precisely. So the first thing I want to do is introduce this notation, right? This is half closed interval from 0 to s, where s is a nested tuple. And this is our notation just for the collection of nested tuples with the same profile. So in other words, if we look at the profile of something like 3, 2, 2, this would be equal to the profile of 1, 1, 4, or something like this. Profile means nesting pattern, pattern of parenthesization. So this notation just means you look at the collection of all nested tuples with the same parenthesization pattern, such that each entry is, well, non-negative and strictly less than the corresponding entry of our shape tuple. This definition might look a little abstract, but on the next slide, we'll see an explicit example of a particular nested tuple together with all of the elements in this corresponding set.
Where does name profile come from here? Like, what is it? Like, what's the intuition?
Profile, I don't know. Jay, do you have a suggestion of where this name came from? It's an invariant of the nested tuple somehow. It contains, it is precisely like the complement of the underlying tuple. In other words, a nested tuple specified by a tuple in a profile. But as far as the terminology, yeah, I'm not sure what the.
I think the nomenclature profile is quite natural. It's describing. I mean, you're trying to specify what is admissible for the layout as a coordinate. So, in terms of like the etymology of profile, I think it connects in that way.
I define an equivalence relation on so-called int tuples, I define an equivalence relation on hierarchical tuples called congruence, which is an equivalence relation that states that two hierarchical tuples have the same profile. And so you think of hierarchical tuple is a tuple of tuples. If the tree structure of the leaves are equivalent, then they are considered to have the same profile.
Yeah, that makes sense. And in fact, in our paper, we use this terminology as well, that nested tuples are congruent. And in fact, our definition is they are congruent if their profiles are equal. So yeah, this is a nice way to express this as well.
Yeah, precisely.
Cool. So great. So we know now what this symbol means. So let's define the coordinate function of a layout L. So here we're going to suppose that L is some layout. We'll define its coordinate function to be the function whose inputs are these nested tuples of the same profile, whose entries are bounded by the corresponding entry of the shape. And it's going to map to the integers by taking a dot product with the stride. So this is the explicit formula. Here, maybe one might object that dot products are something defined for tuples, not nested tuples, but the idea is, okay, flatten the guys and then take their dot product. Let's be more explicit. Let's take a look at an example of this thing. Okay. So here's a nice layout. Its shape is 3, 2, 2. Its stride is 4, 0, 2. And first of all, I want to say that the collection of all of these elements is this 0 to S in our case. You'll see that these nested tuples look exactly like the shape. It's just that the entries are some integer less than the corresponding entry of the shape. How do we map to the corresponding value? Well, we just do a dot product with the strides tuple 4, 0, 2. So this is exactly 4, 0, 2 dot. And this produces the pattern of outputs on the right-hand side. And so for each of these images, these gray sort of grids of values we saw before, what you would see is that if you took this corresponding input coordinate and did a dot product with the stride, the result would be exactly the number by which that cell in the matrix was labeled. Okay, great. So this is the coordinate function of a layout. And the next observation we want to make is this. The inputs to this coordinate function were nested tuples, whereas the outputs of the coordinate function were integers. So in particular, you can't compose two functions like this, right? The input of this function is not going to be admissible as an input for a different coordinate function, unless, of course, that layout had maybe a very trivial shape. But a key observation of CuTe is that we can actually provide more general inputs to this coordinate function. And so that's what we want to do next, is explain how one might provide, instead of a nested tuple of the same profile as the shape input, one might provide just an integer input, or maybe some other nested tuple of a different profile. So let's make the necessary definitions. In order to do this, we need to just specify or sort of establish a vocabulary so that we can precisely discuss these nested tuples. So we're going to define some important properties by an example. So here's our very generic example of a nested tuple. It has entries, some of which are integers, other which are tuples of integers, others of which are tuples of such things, right? And the idea is that each one of these nested tuples has some modes and has some entries. And these are not the same thing. The modes are the sort of top level entries of the tuple. The modes of this layout are 4, the tuple 5, 5, and the nested tuple 2, 3, 3. Each nested tuple also has entries, which in this case would be, well, the integers 4, 5, 5, 2, 3, and 3. It's important when one is discussing or defining or doing some construction with nested tuples that one keeps clear the concept of mode versus entry. There's some other important attributes of nested tuples that we need to be able to discuss. So the number of modes that a nested tuple has is called the rank of the nested tuple. So in this case, we have 3 modes. So this is a rank 3 nested tuple, or a rank 3 shape. On the other hand, the number of entries in a nested tuple is the length of that nested tuple. So earlier on, like whenever we saw this big matrix example, this interleaved layout, that thing was a rank 2 layout, but a length 4 layout. And so somehow the length is capturing all of the integer values, whereas the rank is just telling you the sort of top level logical shape. Finally, we need to define the size of a nested tuple. And the size of the nested tuple is just going to be the product of its entries. So for example, if our nested tuple is just m comma n, then the size is going to be m times n. This is telling you the number of cells in the corresponding sort of higher dimensional array. Okay, so this is sort of this just gives us some footing to be able to discuss these things a little more precisely. What we want to do next is talk about how we can provide more general inputs to this so-called coordinate function of a layout. In order to do that, we need the following definition. And this is that of refinement. So here we'll say that a nested tuple S refines some other nested tuple S prime, and we'll denote it by drawing a double-headed arrow from S to S prime. If S may be obtained from S prime by replacing some of its entries with some other nested tuples of the same size. And so a very generic example of this thing, and we'll see some more examples on the next slide, would be something like this. So maybe we start with an S prime on the right side, which is something like 4, 25. And a good example of a nested tuple S, which refines this nested tuple S prime, would be something like 2, 2, and 5, 5. So the point is that we can see that somehow we've obtained S from having replaced each entry, or we've obtained S from having replaced each entry of S prime, in this case 4 and 25, by some other more general nested tuple, which has that same size. 2, 2 has size 4, 5, 5 has size 25. I want to mention here that in the CuTe documentation, you might say something like compatible with to describe this sort of relation. Here we're avoiding the terminology compatible with, because compatible with sort of suggests maybe a symmetric relation, whereas this is sort of not a symmetric relation, right? If S refines S prime probably does not refine S, and one could say something more precise about that. But in any case, if you're reading the CuTe documentation and trying to match that up with what we're saying here, this is sort of the translation. Okay, great. So let's look at a larger example, right? Earlier on, we were looking at this, earlier on, we were looking at this layout whose shape was nested. It was 2, 3, 4, 2. Here in this picture, we've drawn the collection of all nested tuples which are refined by that shape S. So here we have this big sort of diagram of these double-headed arrows. We can see that if you zoom in on any particular double-headed arrow, such as this guy, well, we'll see that, oh, okay, the nested tuple from which the arrow emanates is obtained from the nested tuple to which the double-headed arrow points by replacing this entry 6 with the entry 2, 3, and by replacing 8 with, well, 8. It's unchanged. I should also mention that when we depict a picture like this, somehow we are suppressing some of the arrows. The idea is that, well, there's an arrow pointing from 2, 3, 8 to 6, 8, and then one pointing to this 48 on the bottom. And sure enough, there also ought to be some arrow pointing in this direction. In other words, in some sense, we can compose these refinement relations. We can make this more precise once we start talking about categories. Here you're seeing categorical concepts naturally arise. Here we have some sort of morphisms or arrows between certain objects, and we're able to compose them in some well-defined way. In any case, what we'll see is that if we have a layout with shape 2, 3, 4, 2, it turns out that we could provide that coordinate function with inputs from the set corresponding to any of these guys in this picture. Let's see what that looks like. In order to make this precise, we need a technical definition. And that definition is that of the colexicographic isomorphism, a highly fancy word, but it defines a very simple concept. The idea is that if we have some nested tuple S of size n, well, then we can linearize the collection of elements in this set from 0 to S. And the way we do it is as described by the formula shown here, right? Now, this is a precise and mathematical definition, but maybe a key observation is that this is exactly the coordinate mapping of the generalized column major layout. So what we're doing is we're just linearizing our collection of nested tuples by ordering them, starting with the first mode, then the next mode, then the next mode, etc. So let's look at an example of this thing. So here we're going to again look at our shape 3, 2, 2. Let's look at what the colexicographic isomorphism looks like in this case. So here we've listed out all the elements in the interval from 0 to S, and we've shown to which integer they correspond under the colexicographic isomorphism. And so maybe what you should look at is the fact that on the right-hand side, our values are listed from 0 to 11 in increasing fashion. And then on the left-hand side, we say, oh, okay, we're just increasing the first entry, the initial entry, until its maximum value. And then we're increasing the next entry. And then we're increasing the next entry. Maybe I should just say this and this. 0 to 1. And so if you like, you might think of these as sort of like mixed base numbers in some sense, right? We're we're corresponding, or we're writing each integer in the range from 0 to 11 in sort of this mixed base. In any case, this is just a canonical way to linearize this collection of nested tuples. And we're going to use this for a lot of our constructions. Okay. So the key point is that not only do we have a colexicographic isomorphism from the set from 0 to S to the size of S, we actually have it for any refinement more generally. And without being too precise, the point is that you can just sort of apply this formula entry-wise. The definition of refinement said, okay, certain entries are replaced by more general nested tuples. And so you can sort of stitch these colexicographic isomorphisms together to define a colexicographic isomorphism like this one shown here. The result of this observation is that if we have this thing here, right, this was the collection of refinements of our shape S equals 2, 3, 4, 2. Well, we knew that we could feed this thing into the coordinate function for our layout L, valid input for coordinate function of L. But because we've identified nested tuples of this form with all these other nested tuples, we can also say that all of these guys are also valid inputs. In other words, if we want to evaluate our coordinate function, if you will, on the integer 20 rather than some nested tuple, well, we just ask ourselves, to which nested tuple of the same profile as S does this integer 20 correspond under the colexicographic isomorphism? And then we'll just take the dot product of that thing with the stride D. Great. So we've seen that we can feed this coordinate function more general inputs. And in fact, maybe the kind of inputs that we care the most about are integer inputs. This is sort of like the minimal thing, which is refined by our shape. And so let's take a second to specify what is, or rather we'll give this function a special name. We'll say the layout function of a layout L is, well, the coordinate function, but where we provide it only integer inputs. And so precisely, it's given by this diagram with the corresponding formula, right? If we have any integer which is less than the size of L, we will just fold it into a nested tuple of the same profile as S according to the colexicographic isomorphism, and then we'll take a dot product with the stride D. This specifies a map from some interval to the integers. We'll denote this map capital Phi L. So maybe things have gotten a little abstract. I want to make sure that throughout this talk, right, we're going to like maybe develop some more advanced concepts, but I want to sort of return to basics periodically so that we can continue to sort of gain from this, and maybe we don't get lost in too many of the technical details. So let's take a look at this example. So here's a layout. It's the row major layout of shape 5, 3. We might ask, what is the layout function of this layout? And the answer to that is, well, okay, if I want to feed it some integer like 11, that's a valid input. It's between 0 and the size of L. Well, I'm going to look at which tuple in 0, 5 cross 0, 3 does this correspond to under the colexicographic isomorphism. And I would say, okay, well, 11 is made up of 2 5s and 2 5s plus 1, right? So this corresponds to the tuple 1, 2. And so we take that 1, 2 and do a dot product with the stride 3, 1. That's what leads to this answer here, right? We do 3 times 1 plus 1 times 2, and that gives us an answer of 5. So this is an example of how we compute the value of the layout function of some layout at some integer input.
So another way that I like to think about this that is kind of convenient is you've talked about transforming between coordinate what I call coordinate sets or coordinate lists. Transforming between coordinate lists with some bijective function, which happens to be your colexicographic isomorphism. That only depends on the shape. And so ultimately what you're saying is that the shape itself is a function that is mapping from these coordinate sets to what we call the natural coordinates, which are these maximally refined coordinates, which match the profile of the shape. So if the shape is a function that maps to these natural coordinates, then you can also interpret the stride as a function from natural coordinates to perform this inner product to these offsets. And then a really nice way to think about it is that layouts are functions. Layouts themselves are the composition of the shape function and the stride function.
Yeah, that's a very nice way to put this. And just to connect that to what we see in this diagram here, right? According to Chris's terminology, this is sort of the shape function. This is the function defined only by the shape of the layout. And then taking the dot product, the stride, is sort of the function you get. This is, I guess, what Chris called the stride function. Yeah. This is a nice way to conceptualize this sort of construction. Great. Okay, so let's continue on. We've defined layout functions, and we've seen a good example of a layout function. What I want to pivot to next is, well, more general operations one might do with layouts, right? Or actually, operations one might do with layouts. We saw that we might be interested in, for example, taking a matrix and tiling it into tiles which might be owned by various agents, like clusters or CTAs or threads or something like this. And it turns out that these interleaved layouts, which you need, arise naturally via certain algebraic operations. Most importantly, logical division and things like logical product and various variants of these. And so I want to turn to a discussion of these operations. So first, let's take a look at an example of logical division before we define it. So here we've got some nice pictures of a layout A, of a layout B, and then of the logical division of A by B. We see that A itself is a column major layout, right? But each column is contiguous. B is also a column major, or rather B is a strided layout. But in any case, the point is on the left-hand side, we've sort of colored each 2x4 tile of this layout according to B, right? We could take this layout B and tile the matrix A with it. The resulting layout, A logical divide B, well, let's figure out what sort of the shape of this layout is. So here we might say that this guy has shape M by N. Maybe this guy has shape tile M by tile N. And what we see in the logical division is that this first mode has shape tile size. So this is like tile M times tile N. Whereas this other mode over here has size what we might call rest M times rest N. In other words, rest M is M divided by tile M. Rest N is N divided by tile N. And so what we're doing is we're decomposing the layout A into tiles, where if we look in this picture on the right-hand side, each column is just an individual tile of A. Each row is giving you a fixed index of all of the various tiles. So for example, maybe let me connect that with sort of how this picture was produced, right? We see that the columns share a hue, right? We have a red column, a yellow column, a green column, etc. This corresponds to the red tile, yellow tile, green tile, etc. And then if we look at the layout B, right? Each cell has its own opacity. We have a very lightly shaded 0 all the way up to a very darkly shaded 19. And we see that this corresponds to the fact that the initial row of our logical divide has the lightest opacity, and the final row of our logical divide has the darkest opacity. So at the end of the day, the point is that here are our tiles, and then here are our entries within a tile. Okay. So here's sort of a visual example of logical division. it's an important operation. There's another important operation called logical product, and it is in some sense inverse to this, right? The idea is, well, maybe we start with some tile A. Maybe let me write this down. Maybe we start with a tile A, and maybe we have some arrangement of tiles specified by B. And we can take a logical product, which produces this layout we see on the right-hand side. Again, we see that each one of these columns represents a tile, and each one of these rows represents entries within a tile. Okay. So these are examples of logical division and logical product, but we should probably specify what they actually are. So let's take a look at a definition. The logical division of A by B is specified by this formula here. And the logical product of A and B is specified by this formula here. And if we look at what these formulas are telling us, they're telling us that these logical divide and logical product operations are themselves defined in terms of more fundamental layout operations. Let's see what those are, right? Here we see composition. Here we see what's called complementation. And then, of course, we're taking the result of some operations like that, and we're concatenating them together. Similarly, if we look at this bottom definition here of logical product, we'll see that we do some composition, we do some complementation, and we concatenate some layouts. Very good. So the point is that if we want to hope to understand, or if we want to understand logical division and logical product, what we really need to do is understand these other operations. We really need to understand what is composition and how do you compute it, what is a complement and how do you compute it, and what is concatenation, how do you compute it. Maybe that last one is the easiest one. But in any case, that's what we're going to do. We're going to take a look at each of these sort of more primitive operations and give some definitions and examples so we can understand these a little bit better and hence parse these formulas which define logical division and logical product. I'll mention here that there's another operation called coalesce of layouts, which we're going to discuss. It doesn't appear explicitly in this formula, but it's important to understand here and elsewhere during the talk. So we will visit that so we can understand this operation that if you've worked with CuTe for a while, you've likely seen before. Okay, great. So let's start with composition, which by my estimation is the most fundamental and important operation on layouts. Let's define composition. So if A and B are layouts, then the composition of A and B is in particular a layout, which we denote by that symbol, satisfying these two properties. The first property is that the shape of this layout refines the shape of A. Okay, great. We understand what that means. It means the shape pretty much looks like the shape of A, but we might have decomposed various entries. In other words, we might have factored various entries of the shape of A into some more general nested tuples. The second property, and the suggestive property, is that if we look at the layout function of this supposed composite of A and B, this is exactly equal to the functional composition of the layout function of A with the layout function of B. So maybe this is the most important property that you want to keep in mind, right? Composition of layouts corresponds to composition of their layout functions. It's also worth mentioning here that this isn't really a full definition yet. Or maybe if we defined composition like this, we should say then a composition of A and B is a layout satisfying this property. If you want uniqueness of this, you need to impose some additional formulas or some additional conditions. But maybe we'll elide that for the purpose of this talk. And we encourage the audience to think of this property number 2 as the essential property. It's some layout whose layout function is exactly the composite of those of A and B.
I make the distinction between functional composition and group composition, because we can always represent the functional composition, right? I can just evaluate A and then evaluate B, and call that another function and evaluate that function. So that's what I would call functional composition of any two functions, including layouts. Whereas this definition is, I make the distinction that this definition is for group composition. This is where we have two layouts. We want to produce another layout which represents the functional composition of those two layouts. And that I call the group composition, because we're creating another layout. And like you said, that doesn't always exist.
Sure. So in other words, are you saying that this symbol represents grouped composition?
Not grouped, just group, like an algebraic
group. Groups.
Yeah, group composition, and then your phi symbol there is essentially saying, think of this layout as a function. This is the functional composition. So you have group composition on the top and then functional composition on the bottom.
That's right. Okay. Yeah. Thank you for sharing this. Yeah, maybe an important takeaway in any case is that, right, we're using the same symbol in two different contexts, right? Whenever we write the little circle between A and B themselves, that's not the same operation as the little circle that we write between just two functions from integers to integers. Here we're defining what the little circle here in the central expression is in terms of the
and to answer questions in the chat too, this is not actually a group. that's a misnomer as well, because there is not always a layout that represents that functional composition. This is not a closed group. And so you can break this, but it's but it works often enough, and it's useful enough that we found a ton of applications for it.
Yeah, great. Yeah, thank you, Chris. And very soon we're going to take a close look at these subtleties involving composition of layouts and why you can't just grab any two layouts and just throw them together and compose them and expect this to work out. There's sort of certain properties or certain conditions which must be satisfied. So in any case, let's take a look at an example of this thing, right? So let's look at the layout A here and the layout B shown below. Each of these happens to be a row major layout, right? Why is it row major? Well, because each of the entries in the stride look like prefix products of the entries in the shape. And we start with 1 on the far right-hand side, and then we move to the left. In any case, the claim is that the layout composition of A and B is given by this expression here. Why is that? Well, you could call like CuTe.composition on these layouts, and this is what's returned. And so maybe we don't know how to compute it ourselves yet, but we could at least check that it satisfies the claimed property, right? So let's take an input and let's feed it to phi A and then feed the result to phi B and see if that's really the same as what we get when we plug that input into the layout function of A followed by B. So that's what we do here, right? We want the result at the end of this top computation to be equal to the result at the bottom. And we see that, okay, if we take 3, we expand 3 colexicographically to get, of course, to get 3, 0. Switch the order of these things. And then we take a dot product with 6, 1 to get 18. Okay, cool. 18 is an integer. And so we can feed this into the layout function of B. Again, we'll sort of fold this 18 up colexicographically into this tuple 6, 1. We'll take a dot product with the stride 4, 1, and we get an answer of 25. Okay. On the other hand, let's look at this claimed composite of the layouts A and B. Well, I can take this input 3, and I'll go colex inverse to obtain a nested tuple of the same profile as the shape of this layout, which is listed above, A followed by B. In this case, it's 1, 1, 0. I'll take a dot product with the stride of this layout, and we see that we again get 25. Okay, so this seems to be the case, right? Of course, to check that these functions really are equal, we would have to test at every input. So how do you actually come up with the composite? It's not so clear, right? here we started with two very simple layouts, right? Two row major layouts. And we see that the answer is not row major, it's not column major, it's not flat, right? It's some strange sort of interleaved layout. And maybe one of the goals of our talk is to sort of demystify this thing and try to explain why these sorts of nested layouts arise, even when you compose very simple things. Great. So that was composition. And recall that in this portion of the talk, over the next few slides, we're just going to list out some of the important operations on layouts and give definitions and examples, right? So let's see all of them. But after that, we're going to sort of move on to a separate topic. Well, maybe not a separate topic, but the next topic. So let's briefly specify what concatenation is. This is a nice simple layout operation, right? If you have two layouts L and L prime, you can concatenate them by just forming a tuple of L and L prime. In other words, the shape of this concatenation will be obtained by concatenating the shapes of the layouts L and L prime. And the stride of the concatenation will be the concatenation of the strides. So this is nice and simple. As an example, if we take this L and this L prime, then we get this L comma L prime. So this is a very natural sort of operation. Let's maybe move on to one that's a little more subtle. Let's take a look at the operation of complementation. So let's suppose that L is a layout.
I'm sorry, Jack. Just like more of a Neanderthal question. Like in concatenation, does it also like literally map to like geometric, like sort of like actual concatenation, or does it mean like something slightly different for the layouts here?
It depends on what you mean by geometric concatenation. Maybe one thing I will say is this, right? S and S prime here might be shapes which are sort of high dimensional. But when we concatenate them, if we look at the sort of top level logical shape, this thing will be 2D, right? It will have its first mode, or its initial mode will be like the full shape of S, and then its second mode or its next mode will be the entire shape S prime. Does this address your question?
I believe so. Yes. Okay. Yeah.
Okay. Yeah. Please share more questions or comments as they arise if you'd like.
There is slightly an interpretation. So, yeah, when you say concatenation to people, most people interpret that as, okay, I'm going to take an array of length 5 and an array of length 7 and concatenate them and get an array of length 12. That is not the kind of concatenation that we're talking about. We're talking about more like tensor product or Kronecker product terms. And so if I take a layout of size 5 and I concatenate that with a layout of size 7, then what the result is should probably be interpreted as a matrix of size 5 by 7. So I'm in some sense, you're kind of multiplying the layouts together in this concatenation. You're upping your rank. You're reproducing the first layout across that second layout. But that's not quite what you think about when you think about product either. So I don't like using that term as well.
That makes sense though. Like, but then the notation necessarily. So you mentioned that, like, basically knowing that you would increase the rank by doing this operation. Would that be clear from this notation? Like, basically, how could I guess yes, because I would look at the values of the first tuple, and as long as those are going up after the concatenation, then I know that the rank went up. Which it didn't in this case, right? Because
right. Right. The rank is not going to increase when you do this. Well, I guess it might, depending on the rank is always going to be 2 if you do this binary version of concatenation. But what will increase is the length of the layout. And so this is this distinction between modes versus entries, rank versus length. Here you'll have a layout of greater length, and unless you have some trivial size, a layout of greater size. And in particular, maybe we should write that size of this guy, L comma L prime, is going to be equal to the size of L times the size of L prime.
Oh, I see. Yes. Okay. Now it's clicked. Thank you.
Yeah, wonderful. And maybe just as a further aside, it's worth noting that, right, I said something about binary concatenation, right? This concatenation operation is not associative. So in other words, there are multiple ways to concatenate three things together. If you sort of do the ternary concatenation, like if you do something like L prime, L double prime, this is not literally equal as layouts to something like L prime, L double prime. And that is also not equal to something like L prime, L double prime. And so the profile we use sort of matters when we do constructions like this, is the takeaway. Okay, cool. So great. So this is one of our sort of fundamental operations of concatenation. Next, we're going to turn to what is the complement of a layout with respect to an integer. So we'll suppose that L is a layout and N is an integer, and we want to define the complement of L with respect to N. And we're going to characterize it by a couple of properties. Again, here we've omitted maybe an additional property or two, which will guarantee that this thing is unique. But these are the essential properties of complement, right? The point is that the complement of a layout L with respect to N will be some layout such that if we concatenate with L, we get a compact layout. Where compact, I mean, there's a few different ways to say this. We could say that its layout function is a bijection. Again, this is a slight misnomer. So here we'd have like, well, maybe let's just be precise, right? Let's say define. If A is a layout, then A is compact if, when we look at this function from the 0 to the size of A, this is the layout function, it's going to map a priori to Z, this is phi A. Well, this is a compact layout if this guy happens to factor through this interval here, and this resulting map is a bijection. I don't know, maybe this is like the mathematician in me who wants to write a diagram like this. But the point is just that maybe a better way to say this is if you look at one of these grids which represents the layout, you want each integer between 0 and the size of A minus 1 to be represented exactly once. This is a compact layout. So things like row major layouts, column major layouts, permutations thereof, these are compact layouts. And in fact, in our paper, you can find sort of a list of equivalent property or equivalent characterizations of compact.
So I agree. This is a totally useful definition of complement that has a lot of really nice properties associated with it. All of those properties are not always wanted or desired. You don't need compactness of the sort of completed layout all the time. And so in the paper, I have actually a more general definition of complement that doesn't have that second parameter. So there is no with respect to, which is really nice and simplifies everything greatly. The only place where you do need this compactness constraint is when you're using it in particular divide operations, and you don't want to lose elements of the target layout. So I call those I don't have a real name for those. I think I have oh yeah, I do, but it's too much. I don't want to spam you with verbiage, but yeah, these particular, this complementation constraint only is required in very particular applications. And so it's not part of my more general definition of complement. So anyway.
I see. So yeah, so maybe we can direct the audience to Chris's paper to see his discussion of and development of complement in that context. Right here, we're using this definition of complement of L with respect to N. I guess what I would say is that, right, yeah, this is maybe, yeah, useful. It's certainly useful for certain things. And in our paper, we have a discussion of these complements and develop some important properties. Like in particular, like there is a minimal N with respect to which this thing exists, and we characterize precisely when a layout L admits a complement, and in that case, with respect to which N's does it admit a complement. But yeah, maybe maybe the audience should check out. And in fact, I very much plan to check out this alternate definition. There's also another paper about integer set relations by a team at NVIDIA. And I'll plug that at the end of the talk. I know they define some other variant of complement. I'm not sure if this coincides with the version you're talking about, Chris, or not.
I think their version is my older version, which is similar to this. But.
I see. Okay, cool. So in any case, for us, this is our definition of a complement of L with respect to N. We want the concatenated layout to be compact. So this is sort of filling in the gaps, if you like, of the first layout L in some sense. And then it's a complement with respect to N if, well, the size of the concatenated layout is N. So the idea is that, well, L together with its complement is exactly a compact layout of size N. So let's take a quick look at an example. So here, maybe our layout L is this guy here. This is 3, 7, 2, 30. And maybe N is this integer 210. Well, we claim that the complement of L with respect to this N is given by this formula. How can we check that? Well, we concatenate them and we check that the two properties are satisfied. And in this case, well, is this thing compact? I mean, you don't want to go from first principles and try writing down like all the values of the layout function. What you can do is look at this thing and see that this is in fact a generalized column major layout, right? We can see that here we have like a contiguous dimension, and then we just stride by that previous shape 2, and then, or sorry, that previous shape 2, and then we stride by the previous shape 6, and then we stride by the previous shape 5. So anyways, the point is that you can identify that this thing is compact by observing that this thing is a reparenthesization of a generalized column major layout. These permutations of column major layouts, if you're used to using CuTe in practice, this is like the result of calling something like CuTe.makeOrdered layout with some permutation.
So let me just take a second to motivate some of this stuff, because I think that's getting lost. At a high level, what is complement trying to do? It's trying to give you it's trying to give you everything that another layout does not give you, which you can imagine is very, very useful when you want to do some sort of tiling, right? If I have a big tensor of data and I want to extract out a certain tile, then it's useful to extract out everything that's not that tile as well. And so complement is everything that is not that tile. And it turns out that the complement of a layout is very often a layout itself. And so you can think of like a tile of grids, or excuse me, let's flip it. Very often we think about grids of tiles, right? And so if I specify a layout that describes a certain tile, then the complement of that tile is very often going to be the layout of the grid, which jumps between my tiles. And so you can imagine this is very, very useful, and it's why it's a core component of logical divide. Logical divide is splitting one layout according to everything that another layout specifies. So this layout tells me all of the elements to extract from this layout, and then I want all of the elements that are not extracted by that layout. And so divides a layout into two pieces: everything that is included in the layout and everything that is not included in that layout. And that's why complement is so important. And honestly, complement is one of the hardest layout operations to like pin down. Yeah, filling the holes. Complement itself is one of the hardest algebraic operations to kind of like pin down. And that's why there's this like extra term in some of my old definitions, and it's kind of changed the most, and it has these different constraints based on how you're using it in different ways and such. So,
yeah, thank you for that, Chris. So right, so we should certainly recall, right, that the reason why this complement came up at all in the first place is because it arises in the definition of logical divide and logical product. And this is exactly why it arises. It's because we have some tile, we have some arrangement of tiles, and we have the full tensor. And somehow logical divide and logical product connect these three guys together in one way or another. Later on, we're going to, right, as Chris mentioned, this complementation is very subtle. Like, hey, how do you sort of compute this guy? How do you define this guy properly? I'll advertise that later on in the talk, we have this sort of nice mathematical formalism for working with complements as they're defined here. And so in practice, if you have some layout, you can compute its complement by hand in a very intuitive way. In particular, we'll compute a bunch of examples by hand later on, and hopefully the audience will find this useful.
So Jack, on this slide, you swapped L and L prime. There's a question about this, right?
I swapped L and L prime. Oh yeah, so I think maybe it wasn't a swap, but maybe it's an omission. Maybe I omitted L prime equals this.
No,
are you saying out here?
Yes.
I see. My apologies. Yeah, so maybe I would say that being compact is invariant under permuting things. That would be a fancy way to say it. The low level version is that you can check the condition on L comma L prime or L prime comma L. I did not intend to switch these. This was a typo. So let's unswitch them. Let's let this be L, where of course scratching out an apostrophe sort of just results in a fatter apostrophe. So my apologies, but yeah, maybe the initial guy is L prime and the next guy is L. Okay, great. So let's continue on. Maybe I want to keep the timing of the talk in mind. So maybe we'll just move rather quickly through this. There's another operation called coalesce. It's an operation which takes in a layout L and produces another layout coalesce L. And the way that we do it is we, first of all, flatten L. In other words, throw away the nesting. And then we're going to consolidate adjacent modes when they satisfy a certain condition, namely the product of a shape and a stride entry are equal to the next stride entry. Maybe the formula written here isn't particularly motivated, but later on, in fact, with our categorical formulation, we'll see sort of a simple reason for which this is a useful and natural operation. Maybe the key point of coalesce is that you are simplifying the layout without altering its layout function. A maybe more highfalutin way of saying this is that having identical layout functions is an equivalence relation on layouts. And this coalesce operation is sort of picking out a canonical representative, the simplest representative of its equivalence class under this relation. So take whichever version of that you like. But this is sort of the operation in a nutshell. We'll see another take on this later on. So, right, what does this look like in practice? Here's a layout. If the entries in this layout satisfy a certain property, in this case, we see, oh, wait a second. Wait, hold on. Which ones got combined? 2 and 3. Yeah, that's right. 2 times 1 equals 2. This is like SI times DI equals DI plus 1. So that means we can combine these modes. As maybe an exercise to the audience, I would encourage y'all to think about what it looks like when you take a column major layout and coalesce. There's sort of a nice description of this thing. So we've reviewed the basic and fundamental operations of layouts. And I want to sort of turn our attention back to layout composition. This is maybe the most essential operation, which underlies a lot of the things that we want to do. And the point is that computing composition of layouts is something subtle, right? We saw an example, but like, who knows where that layout composition came from or how we knew to sort of write this formula down. So let's maybe make clear these subtleties. So the point is that if we have a layout, say A, then the layout function of A has this form, right? It looks like you take your interval 0 to m, you take the colexicographic isomorphism, and then you do a dot product with the stride. And in fact, a layout is precisely specified by a function together with a factorization like this. So here we have colex, and here we have this stride. So this is like some multilinear function, linear. But the subtlety arises for the following reason. If we have an A and we have a B, we can definitely compose those functions phi A and phi B, right? Just plug an input into phi A, take the output, plug that into phi b, and look at what you get. That's the composite of phi a with phi b. But the problem is that whenever we compose these guys, it's not always possible to express the results in this nice factored form of colexicographic isomorphism followed by stride. And this problem of trying to rewrite such a composition in this way is exactly the problem of trying to identify a composition of layouts A and B. So this is sort of the central question, right? If we have layouts A and B, can we actually factor these guys as some colex to some shape followed by dot product with some stride, right? And it turns out that this is not always possible. And maybe that's one of the motivations of developing some of the work we'll discuss later is we want to identify, like, when is it possible to compose layouts A and B? Can you tell just by looking at the shape and the stride of a couple of layouts whether or not you can compose them? Moreover, can you actually compute what the layout composition is in some sort of reasonably intuitive way? Okay. So this sort of motivates the following work. Let's recap what we did. This is sort of us coming to the end of the initial section of the talk, which is sort of a broad overview of, what are these CuTe layouts? What are the operations they support? Let's look at a few examples. So what have we learned, right? We learned that layouts are important. They're used to specify how our data is well laid out in memory. And it's also used to manage this hierarchy of threads that one has to sort of grapple with in GPU programming, right? We have to take our tensors and partition them among clusters and CTAs and threads. And it's a lot to manage. And these CuTe layouts do a lot of that heavy lifting for us. We've seen also that in order to do the sort of things we want to do, we need to work with, logical division and logical product. That's what allows us to decompose our operands and our outputs into smaller pieces that can be handled by various agents like CTAs and threads. And these themselves are defined in terms of more primitive operations like composition and complement. This is sort of the summary of what we've learned so far. And so what we're going to do next is change perspective a little bit. What we're going to do is we're going to restrict our attention not to all CuTe layouts, but just to a slightly smaller collection of layouts, which we'll call tractable layouts. And the value of this is that these tractable layouts are still expressive enough to support a lot of the stuff we care about, right? We can permute tractable layouts. We can slice into tensors using these tractable layouts. They support broadcasting, partitioning, all the sort of things that you'll want to use in practice. But the upside is that if we don't allow sort of arbitrary layouts, in other words, if we don't allow arbitrary strides, we can write down a very simple theory, which sort of exposes how this layout composition works in practice and also exposes a lot of natural operations we've seen like complementation and coalesce, etc. So let's quickly define what is a tractable layout, and then we're going to start using some cool machinery from category theory, if you like, in order to describe these in a very sort of algebraically natural way. So here's a definition of tractable, right? We'll say L is tractable if L can be obtained from a column major layout by permuting the modes, by possibly removing some modes, by possibly inserting some modes with strides equal to 0, and by possibly reparenthesizing. So this is sort of like a generators and relations definition, if anyone is familiar with this from abstract algebra. It's like we're using the column major layouts as generators, and then we're sort of looking at the span of these under this action of permuting and removing and inserting and reparenthesizing.
There's another nice definition of this, which is, it might be a vocabulary dump, but a layout L is tractable if the completed layout, which is the concatenation of L with its complement, has a reflexive generalized inverse, which means it has both a left inverse and a right inverse, which I do detail in the CuTe paper as well. So rather than these primitive operations, we would prefer to define this in algebraic terms. And there is a nice algebraic statement for these.
Yeah, very nice, right? I guess there are many definitions of this concept, and I guess it depends on like what is the purpose of the definition, right? This definition we give here, this is for the purpose of general audience being able to understand what these layouts are. But yes, for example, in our paper, we don't use this definition. We use a slightly different one. But this is interesting that this has arisen in your work, and we'll certainly check and take a look at this characterization you've given in terms of partial inverses. So great. So yeah, thank you, Chris. So yeah, maybe a point is that these tractable layouts are sort of, they can be described in terms of this generators and relations approach, but maybe can also be characterized abstractly. And then as this remark suggests, you can also give just an explicit sort of element-wise divisibility condition to check this.
But it also tells you why tractable layouts have appeared multiple times. It's because the tractable layout definition actually includes this statement that it has complete right inverses and left inverses, then the subalgebra of elements that are tractable layouts or have tractable layouts do come very, very close to forming an actual group. And so you actually have this really nice group structure where you actually you're guaranteed to have inverses, at least you're guaranteed to have some version of an inverse. And you're much closer to be guaranteed to always have composition, but that's not even true all the time.
I see. Okay, very interesting. Yeah, you mentioned it's like a group, but not quite a group. I mean, does it specify, or does it have have some particular algebraic structure that's sort of
it's like I don't know exactly what it's called, but
right, there's this zoo of things like magmas and monoids and commutative and associative.
But because of this inverse guarantee, you are very close to being a group.
Yeah, very nice. Yeah, thank you, Chris.
What's the intuition? I think, sorry, just as part of your back and forth, like, what's the intuition for composing a layout and its complement? Is this like sort of like an identity op, or is like something more subtle? Like an identity layout transformation, where you just don't change anything?
I don't know, Chris. Why would one compose a layout with its complement? Is this a common operation? I don't know that I've seen.
Compose a layout with its complement, or compose a layout with its inverse.
I think you mentioned the complement when you were referring to the sort of you mentioned some later comment around some right versus left.
So the intuition is that remember this complement is kind of casually defined as filling in the holes, right? Mm-hmm. Let's try and devise a layout that includes everything that the other layout doesn't include. Mm-hmm. And so the tractability and the inverse constraints for that say essentially that if you have a tractable layout, or if you have these inverses exist constraints, then what you can say, which is really convenient in a lot of cases, is that the complement includes everything that the layout doesn't include. And so that everything property is really powerful, because now you can guarantee that you're not like missing any elements in the codomain of these layouts. You're not losing any information in any of these divides. Really nice properties pop out of that. So that's where that kind of thing comes from. Is like guaranteeing that that the complement includes everything that a layout doesn't include.
Yeah, thank you, Chris. Yeah, and just to be clear, in our formulation here, right, we are restricting only to these complements, and this is compatible with CuTe in that all the statements we're saying will be true. You know, if you took these layouts and evaluated them with CuTe.complement, you would get what is returned. But perhaps one might define the complement of A with respect to some other object more generally, which is the idea to which Chris is alluding.
Right. Yeah, and that's what I mean. You don't always need that property, but it is a very powerful property that gives you some nice guarantees.
Great. Okay, cool. So maybe just to give you an idea of what these tractable layouts look like, well, they contain these compact layouts, which look like permutations of column major layouts. They contain nice strided layouts where it maybe almost looks like it's a column major, but maybe we've multiplied by some of the strides by a certain factor. This is an informal description. And also if we have something which looks like, well, a nice row measure, column measure layout that we broadcast to a larger shape, this is also a tractable layout. And this is sort of certainly very explicit based on the definition we gave. This pen is not cooperating. Okay, so this is sort of the end of the first portion of the talk. What we're going to do now is establish some sort of connection. We want to connect this beautiful and novel theory of layouts from computer science to some well-established ideas from mathematics or from abstract algebra. These include things like categories and operands. I'll mention that categories, right, are a very ubiquitous concept, right? They certainly arise throughout mathematics and as well as other fields of science. And they're a very useful framework for being able to, I would say, digest new ideas and to recognize sort of common concepts across different areas of math or computer science or whatever else you may be working with. Before we go into sort of our application of category theory to this layout algebraic stuff, we're going to do a brief review of, an intuitive review of what is a category. We'll take a look at a few examples, and then we'll have the sort of vocabulary we need in order to define our main constructions. I especially encourage anybody, throughout the talk, this is the case, but during this section, if you have questions about these categories or what is this, or aren't you missing an axiom or something, you can certainly ask this, and we are happy to respond. So let's before giving a definition, I think there's a slide before this, right? So the idea behind a category is that it's just an abstraction, which is encoding the notion of composition, some sort of objects, some sort of maps between them, and some sort of composition rule. And sort of the motivating example would be something like sets, right? If you have some sets of elements, you can define functions between those sets. And if you have a function from x to y and a function from y to z, you can compose those guys to obtain a function from x to z. And this is exactly what motivates this definition. So the definition we'll give is that a category C consists of, well, a collection of objects, which we might denote by x and y and z, a collection of morphisms between those objects. We might call those f and g and h, depending on the context. And most importantly, there's some sort of composition rule. So if we have a map f from x to y, so here x is called the domain of f, and here y is the codomain of f. If we have these composable morphisms, we can well compose them to obtain a new morphism whose domain is x and whose codomain is z. So this is the abstract definition. Let's take a look at a few examples that you may or may not have seen before. So let's look at the category fin set of finite sets. So an object in this category is going to be a set of the form 0 to n minus 1 from some n. So it's not containing all sets, not even all finite sets, just these particular sets. And a morphism from one of these sets to another is just going to be any function. So for example, we might have a morphism from 0,3 to 0,4 called f, which might be specified by, okay, f of 0 is 2 and f of 1 is 2 and f of 2 is 3. This is a perfectly good function. No assumption about anything being bijective or injective or surjective or anything like this. The composition of these guys is simply functional composition, right? If I have some input x here, well, if I want to apply this composite map to it, I'm just going to first apply our function f to it, and then I'll apply our function g. So this is sort of the reason for abstracting, right? This is functions and their composition. But not all categories look like sets and functions between sets. Let's take a look at a slightly more exotic example. So here is an example of a category which we're denoting vect. This is a category of vector spaces. And so probably many of you have taken a linear algebra course. If you haven't, that's perfectly fine. But the point is that the objects of this category are the vector spaces Rn for n greater than or equal to 0. So here Rn, this is like the collection of vectors of length n, each of whose entries is some real number. And in this category, a morphism is not going to be specified by a function from Rn to Rm. It's just going to be specified by an m by n matrix. if the domain of A is n and the codomain of A is n. And instead of composing some sort of functions, here our composition rule in this category is just going to be matrix multiplication. So here, A is going to be an m by n matrix, B is going to be a p by m matrix. And so in this case, I could contract along m to obtain a p by n matrix, B times A. And so maybe a key takeaway of this example is that morphisms don't have to be functions. Of course, people familiar with linear algebra might sort of observe that there is a function associated to any m by n matrix, which goes from Rn to Rm. It's like the associated linear transformation. But in any case, a priori, morphisms don't have to be functions. Objects don't have to be sets. Let's take a look at one more example that we'd like to keep in mind before we move on to the other sort of definitions we need. So here's a great example of a category. This is a category which we denote z greater than 0. And in this category, the objects are certainly not sets of any sort. An object in this category is just going to be a positive integer. And what are the morphisms? Well, let's just say that there exists a unique morphism from an object A to an object B if A divides B. And if there's not, then, well, there's no morphisms between those objects. So like, for example, there is a morphism from 7 to 21. And we might give it a name, but in fact, since there's at most one morphism between any two objects, we might just write it like this. However, there is no morphism between 7 and 20. And so one might ask, how do you compose these weird, just sort of divisibility arrows? Well, the point is that composition of these divisibility relations is exactly just an expression of that divisibility of integers is transitive. If A divides B and B divides C, then A divides C. So this is a particular example of what's called a poset category, where here poset means partially ordered set. And so if we want to take a closer look at this category, we have like 1, 2, 3, 4 has a map from 2, and it gets messy very quickly. But here 3 has a map to 6, 2 has a map to 6, etc. So drawing the whole thing is messy. But the point is that this category is exactly the poset, positive integers under divisibility. Okay. So we've defined categories and we've taken a look at a few examples. The key point is just that these categories consist of the data of some collection of objects, some collection of morphisms between those objects, and some rule for composing certain morphisms. We need one more important definition from category theory in order to state all of the theorems we have. And that's the definition of what's called a functor. I'll mention here that, right, you could still gain almost all of what could be gained from this talk without understanding this definition of the term functor. But I encourage you to take a look at this definition and then maybe try to parse the example of a functor we'll see later on. So functors are like morphisms between categories. So if C and D are categories, then a functor f from C to D is going to look like a function from the objects of C to the object of D. So here, each object X and C will map to some object Fx in D. And some other object Y is going to map to some other object Fy in D. And also, this functor is going to assign to each morphism F in the category C some morphism FF, which looks better than it sounds, FF in D. And we don't allow just any old assignment. We need this assignment to be compatible with the category structure on C and D. And so in this case, this would mean, among possibly other things, that if we apply F to the composite of F and G, this better be equal to FF composed with FG. In other words, we could either compose in C and then apply our functor, or we could apply our functor and then compose in D. So we know what a category is, and now we know what a functor is. It's some sort of map between categories. And this might inspire you. You might think, oh, well, like categories are objects together with maps between those objects. So what if we made a category whose objects are themselves categories and whose morphisms are functors? And this is a real idea. And this is something called like a two category. And it ends up leading to a field of study called infinity categories or higher categories. So if you have ever heard this term before, this is sort of the entry point. But maybe that's all we'll say about that for now. So let's at least see one example of one of these functors, and then we'll start looking at the particular examples that are of greatest relevance to us in our work on layouts. So here's a good example of a functor. There's a functor from finite sets to vector spaces, which looks like this. It takes this set from 0 to n, and it maps it to the vector space Rn. And it takes this interval from 0 to m, and it maps it to the vector space Rn. So that's the definition of the functor f on objects. But functors act on objects and also on morphisms. So what is the image of a morphism f under this functor? Well, let's see. F is a function from a set to another set, but this ff is supposed to be an m by n matrix. And in this case, the claim is that we can get a functor if we specify this matrix to have ijth entry equal to, well, 1 if f of j is equal to I and 0 otherwise. This is our definition. And so maybe as a motivating example, you might imagine that f is like a permutation. It goes from 0 to n to 0 to n, and it permutes the entries. In this case, the result would be a permutation matrix. And so maybe as an exercise for the audience, you might try to check the functoriality property of this f. Might check that if you take f and g composable and you apply this formula to the composite function f and g, this is equal to the matrix product. So again, here, this is matrix multiplication, and this is functional composition. Okay, great. So this was our crash course on categories. Let's turn our attention to the examples that are most relevant to us. So the idea is that we want to define some category whose morphisms in some sense correspond to layouts, right? Layouts are these cool mathematical objects that we can compose with one another, at least sometimes. So there should be a way to frame this in terms of categories. One might want a category whose morphisms are themselves layouts or something like this. And so what you'll see for the rest of the talk is our sort of development of this layout algebra and composition and whatnot in this realm of category theory. So for expository reasons, we're going to start with the case of flat layouts. After having covered those, we'll turn to the nested case. Our theory covers both. All right. So great. Here's a category that is of great interest to us. The name of this category is tuple, and the objects of this category are exactly tuples of positive integers. We've certainly seen plenty of tuples of positive integers. These arise as the shapes of flat layouts, and that's no coincidence. Those are the objects. We need to specify morphisms too. A morphism in this category tuple, from some tuple S1 through Sm to some tuple T1 through Tn, is going to be specified by a function from this set to that set. And we don't allow any functions. We only allow functions satisfying 3 properties. And so here are the formulas for those properties. Read them if you like. And on the next slide, we'll see exactly what these properties correspond to diagrammatically. Composition of this in this category is determined by functional composition of these underlying maps, right? So if we have a map F from some tuple S to some tuple T, and a morphism G from some tuple T to some tuple U, well, those lie over some underlying maps alpha and beta, and so we can just compose the underlying maps. And this specifies a morphism in the category tuple from S to U. Okay, so here's the sort of technical definition. Let's take a look at some nice pictures. So here are some examples of morphisms in this category. let's take a look at each of these. So here F is specifying, this picture is supposed to depict a morphism of this form in the category tuple. And the idea is that this guy lies over the map alpha, where alpha of 1 equals 1 and alpha of 2 equals 2. Here the index is sort of corresponding to the height of the entry in this diagram. So this 4, 6 on the left is like a vertical representation of the tuple 4, 6. And similarly for all the other tuples on this page. Similarly, each one of these guys represents some sort of morphism in this category tuple. So maybe just to pick one to expose more explicitly, let's look at this morphism. So this goes from 6, 4 to 6, 2, 4. This is a tuple morphism called H. And this lies over some map, which we might also call alpha if we like, from the set star 1, 2 to the set containing star 1, 2, and 3. And it's given by, well, let's see, the first entry goes to the first entry, so alpha of 1 equals 1. And the second entry goes to the third entry, so alpha of 2 equals 3. So that's how we interpret diagrams like this. And I encourage that the point is that, if we want to do rigorous mathematics, we have to work with the definition on the previous slide. But this is how we think about tuple morphisms. We'll see later on that these tuple morphisms exactly correspond to tractable layouts. Great. I encourage you all to ask questions if you have any, but let's go ahead and proceed on and take a look at some non-examples, right? So here are some non-examples of tuple morphisms. We see for this morphism F, right, that, well, the 4 right here from which this arrow is emanating does not match the 6 to which it points. So this is like not allowed. This is specified by one of those conditions on our definition slide. Similarly, we don't allow multiple entries in the domain to point to the same entry in the codomain. This is not allowed. I guess I should have the same enthusiasm for both of these. Great. So we know what tuple morphisms look like. We know which sort of things are excluded. Let's talk about how we compose these guys. So one of the main points of all of this is that we can do these sort of composition computations diagrammatically, right? If we have a G and an H, which are composable in this category, then we can sort of paste the representing diagrams together, like we've shown on the left-hand side. So here we have like G going from 4, 6 to 6, 4. And then here we have H going from 6, 4 to 6, 2, 4. And what is their composite? Well, it's some map from 4, 6 to 6, 2, 4. And it's exactly the morphism which is depicted by this diagram above, right? So like if we want to know where this 4 goes, well, we look at the 4 in the pasted diagram and we just follow along the arrows. We see this goes to the 4 up top. Similarly here, if we want to know where the 6 goes in the composite map, we just follow the arrows, and we see that this maps to the 6 on bottom. And so composition is very simple in this category. Take your two diagrams, paste them together, and then sort of collapse the arrows, if you like. Contract the arrows. Great. So one might wonder how one for what reason one thinks to write down the definition that we wrote down. And this is sort of just an aside, so maybe this is not so important for much of the audience to think too deeply about. But the point is that this sort of construction where we have objects which lie over finite sets and morphisms which are encoded by sort of underlying maps, this is a standard construction from the theory of operads. And so I just want to mention that, right, just like categories were some sort of abstraction which encodes the notion of composition of morphisms, operads are some sort of abstraction which encodes the notion of n-ary operations and their compositions. And so if you look at some common operads, like you might have, if you're familiar with the stuff, you might know about like the associative operad, the commutative operad, the Lie operad. The point is that their definitions are sort of similar to this definition for the category tuple we'll get. One can say more about this, right? This category tuple we've written sort of arises naturally as a subcategory of a certain operad. It's not one of these well-known ones, but it's some interesting operad which can be constructed from these using some well-known constructions. Cool. So this is sort of the remark for the mathematically inclined in the audience. But maybe let's turn back to the task at hand, right? We're not necessarily category theorists. We sort of care about these layouts and their composition. And so now I want to draw the connection between this category tuple and layouts. The point is that if we have one of these tuple morphisms, we can extract a layout from it. Each of these tuple morphisms encodes a layout. And the layout encoded is given by the formula shown on this slide. So here we're supposing we have some tuple morphism F from a tuple S to a tuple T. Well, we can define from that tuple morphism a layout. The way we do it is by, well, allowing the shape to be the domain of the morphism. And the strides will be equal to either 0 if that element is projected away, or it will be a prefix product. Where here again, you'll notice that we're seeing the underlying map alpha appear in this formula. So as is the case, yeah.
So is this not just saying that layouts are both the objects and the morphisms? Is that ultimately what you're getting at? And therefore this is a 2 category, or am I misinterpreting this?
So I guess what I'm saying here is that there is a layout which can be associated to every morphism. But here we are not identifying morphisms with layouts. Like for instance, there might be more than one different morphism in the category tuple, which gives rise to the same layout. And in fact, we can explicitly characterize the sort of family of tuple morphisms which give rise to the same layout.
Perhaps it's worth noting, though, that maybe what Chris is getting at is it's sort of interesting that the codomain is a shape here, whereas before, like we were expressing a layout as a pair, right, of a shape and a stride, and having a integer valued codomain. But since we need to go to a realm where it's natural to compose layouts, then it becomes natural, like, to think about what should the objects be. We view them as shapes, and the functions then somehow will have to be reinterpreted. Am I interpreting your question right, Chris? Like we'll have the precise connection in terms of writing down like, mathematically a functor, which is what Jack is saying. But like in terms of how the definition is inspired.
I mean, there's a couple of things to say to that. Again, yeah, in the paper I describe shapes as functions themselves, and those functions, you know, take a coordinate and return you back a coordinate. It happens that you can also construct layouts that represent that same function. So in some sense, you can say shapes are layouts.
Yes. So here's how we can understand that in the context of these categories, right? The point is that you're saying that associated to each object, in other words, each shape, there's a layout.
Yep.
Well, associated to each object, there's also a canonical morphism, namely the identity morphism on that object.
Sure.
And this exactly corresponds to what you're saying, that here, if you take the identity morphism on one of these tuples, you'll exactly recover the general, like the column major layout or the layout specified by that shape. And so it is in this sense that like, yeah, right. So sure, the shapes do give rise to layouts too, but it's still sort of secretly coming from a morphism in the category, namely the identity.
And these identities will realize to the colexicographic isomorphism in a sense. Like,
right.
If you, well, anyway, we'll see exactly what the realization functor is.
So I like to quip that one of the utilities of CuTe has been that the layouts are both the nouns and the verbs. And by that, I mean that the layouts are the nouns. Layouts originated as me wanting to describe, you know, data layouts and like tensors. And then slowly I realized that data layouts can be used to describe other things like thread and value layouts, and that those are not quite the same as data layouts. because these are operators. They're partitioning operators, and they are only really used to apply to data layouts. And so layouts are the nouns. They are describing the data distributions, and the verbs. They are describing the permutations and the tiling operations and the slicing and the partitioning stages as well. And to me, that's a nice little beautiful way to wrap that up. And it seems like you're getting at something similar here to me. That's
I think
that's why I said are layouts being considered as the objects and the morphisms here?
Yeah, Jay, did you have a response you wanted to share?
So I was going to say something to the first part and then the second part. So I think we're sort of like the tractable layouts we're thinking of as the verbs, and the tractable layouts like can act on tractable layouts. That's sort of the composition rule, but they can act on more general layouts as well. So
Yes.
like at the end, we'll like just mention that there's a right action of tractable layouts on layouts, which is the more sort of strictly more general formulation.
And that, I agree, is where the utility of tractable layouts comes in as the I was getting my left and right screwed up as the right hand side operator.
Yeah. The pre-composition
layouts, which can be absolutely general, and they can be
absolutely
layouts, they can be whatever. Yeah.
Yes.
I totally agree with that. Yeah.
Awesome. Yeah, there's an analogy with algebra, which is that you might have like a module over a ring. The idea is if you have ring elements, you can multiply those together, but you can also act on elements of the module more generally. And so this is like the tractable layouts are playing the role of like the ring, which is operating on the bigger thing, which would be all layouts.
That's a good point. I have not made that distinction, but maybe I should. That's good.
And cool. Here, I would really say that the layouts in the terms of this category are the morphisms and not the objects. Objects are, I would call the objects the shapes. So we were really trying to write down the category whose objects are shapes and whose morphisms going between shapes are layouts. But as like, and the sort of unusual thing about this definition is viewing the shape as the codomain now. So in that sense, like it's really tied to the tractability assumption.
And there's actually, so that led to my so-called completed algebra as well, which is in the paper, and it's that all of these algebraic operations also apply to layouts that produce coordinates. So if you abstract the strides properly, then you can construct layouts that produce coordinates. And all of these complementation, composition, inverses also apply to those coordinate layouts, which is important. And it seems like you might use in here as well. But good.
Great. Yeah, thank you for the discussion. So let's push forward and take a look at some examples of this thing. We've seen the definition in its abstract, but let's look at these morphisms we saw before and write down what is the corresponding layout. And we'll see that each of these morphisms we see here corresponding to some like very familiar thing. So here, this first morphism F happens to be an example of an identity morphism. And it turns out that these always give rise to column major layouts. So here, let's see, the shape is 4, 6, because that's the domain. And what's the stride associated to 4? Well, let's see. I'll follow the arrow along. It maps to this element. And then I take the product of all elements beneath that. There are none, so that's the empty product. So I just get 1. If I want to know the stride associated to the 6 here, well, I'll take that 6 in the domain. I'll follow it along to the codomain. I get the 6 on the right-hand side. And I compute the associated prefix product. In this case, we're computing the product of all the elements below it, which is just a single 4. And so we get a 4. There's our column major layout. For our next example, right, we have this G. And maybe I'll try to move a little more quickly through these, but I encourage audience members, if you like, to try writing down these layouts as we go along, right? So here we have 4, 6. Okay, let's see. The 4 maps to this 4 up here, and this associated prefix product would be, well, just this 6. And then if I want the stride associated to this 6 here, well, let's see. I'll follow the arrow along, and it maps to the bottom element. And so the corresponding prefix product is, well, the empty product, it's just 1. So here we saw this was like column major. This guy was like row major. And similarly for these other guys, right? Here we have a strided layout. We have 6, 4. And let's see, the 6 maps to this 6, whose associated prefix product is 1. But the 4 does something a little more interesting, right? It maps to this 4 up top, and the associated prefix product now is 6 times 2, which is 12. So here we're getting strided layouts, right? And so one could start to build a dictionary between sort of common concepts we saw in the world of layouts and concepts for these morphisms in this category, right? Like for example, this K right here, if we compute the associated layout, well, we'll see that the stride associated to this 8, whoop, missed an entry. Are you going to let me erase? There we go. The stride associated to this first 8 is, well, an empty product. It's just 1. And then here again, okay, we go over to this 8. The associated prefix product is, well, just 8. And then for the 3, again, by our formula, the rule was if we project away an element. So this means that like in the underlying map, so if this guy lies over alpha from star to 3 to star to 2, then alpha of this index 3 is the base point star. That's what allows us to sort of project away entries. In this case, the stride is just 0, right? And so this gives us like broadcast layouts. Okay, great. So this is how we compute the layout encoded by one of these tuple morphisms. It's important to note that these tuple morphisms do not give rise to arbitrary layouts. As a simple example, here's a simple sort of non-example, we could consider this L of shape 4, 6 with stride 1, 5. If you try to write down a tuple morphism which represents this thing, well, we'll write down the shape 4, 6. 4 has a stride of 1, so we'll just put that at the very bottom. And then 6 has to map somewhere, but then the question is like, what do we put here? Like no matter what we put here, we're going to compute a prefix product, which looks like some numbers times 4. But some integers times 4 is never going to be equal to 5. And so this layout will never arise from a tuple morphism.
So are you implying that I should never use that layout on the right-hand side of a composition? Or
certainly not, right? I mean, the sort of the setting of this, right, is that all CuTe layouts are valuable, but here we're restricting to a particular subset of them and developing a nice natural theory for that subset of layouts. Those layouts happen to be highly expressive to where they'll do almost anything you want. You know, if you like search through CuTe examples and try to find a non-tractable layout, it's not easy to do. But this does not suggest that one would never want a non-tractable layout. In fact, there are concrete places where one does want a non-tractable layout. And in fact, later on, as sort of came up in the discussion, like one can sort of extend this theory to the non-tractable case as well. So yeah, we're not saying layouts like this are never valuable. It's just that we are developing a theory only for those tractable layouts.
I think the only place in which at least I've seen these sorts of layouts arise are when you're describing data layouts, as you were saying. So when you're describing how stuff is laid out in physical memory. But if I'm trying to pre-compose by such a layout, I've never needed to pre-compose by non-tractable layout.
Yeah. I don't know. I can imagine an application that might want to do that for this layout, for instance. So I'm not as willing to say that. But
sure, yeah. It is not the case that non-tractable layouts have no use. Non-tractable layouts have use, certainly. And that being said, in practice, when one is, if one is working with some sort of computations with tensors, right, they're fed in like row major format, and then you're going to do some dividing and tiling, and you're going to distribute among your various agents, and then you're going to during all of these processes, you're sort of closed under this tractability condition. And so it's even though we can't represent explicitly every tractable layout in this form, the theory is still useful. And maybe I should even take it back. Like, it turns out you can represent something like this as a tuple morphism, but it's just sort of a rational extension to this integral story we're telling here. Like, for example, you could write down something like this: 4, 6, 5/4. Now the formula we write down does yield the layout above. And so, in fact, using morphisms like this, where we allow for rational entries, allows one to express arbitrary CuTe layouts using this formalism. Here we're just expressing sort of the clean theory of the tractable ones. But again, this comes up like layout diagrams of this form you can think of as like, these are like the module elements on which you can act by tractable layouts.
Yeah, so this is like a preview of what we were going to say at the end.
Exactly.
With the rational numbers, you can express arbitrary layouts as morphisms.
Interesting. I've used rationals in layouts before, actually, but yeah,
very cool.
Not very common.
Great. Okay, so in any case, right, we've seen some layouts which arise. We've seen not all layouts arise, but the point is that we want an explicit characterization of which layouts are encoded by tuple morphisms. And this is where the tractable layouts enter, right? We can recall our definition of tractable layouts. One definition is that they're the layouts which can be obtained by this column measure or colex layout by possibly permuting, removing modes, inserting modes. And here we're in the flat case, so maybe we're not worried about reparenthesizing. But in any case, we recall that definition, and then we can state maybe our first observation, our first theorem, which is that the layouts which arise from this construction are exactly the flat tractable layouts. We don't have any nesting, but any layout which is tractable can arise from a diagram of the form we've shown. The representing tuple morphism is not unique, but there is, and in fact, let me show sort of an example. Like maybe we want something like 4, 6, 1. Let's see. I'm going to start drawing the diagram to inspire this example. So let's do 4. Let's see. We could have, so 4 times 8 is something like 32. For example, for this layout here, this is a nice tractable layout. It's encoded by this tuple morphism, but it's also, you could do something silly like this. You could do like 2, 2, 2. And so the tuple morphism, which encodes a particular tractable layout, is not unique, right? You could sort of like factor the modes which are not hid. But for this reason, you can just write down like a standard form. Like just don't do any of the sort of unnecessary stuff. Write down the minimal example, and then you get a one-to-one correspondence between what we call non-degenerate flat layout tractable layouts and non-degenerate tuple morphisms of standard form. It deserves to be said, what is this non-degenerate condition? This is just a little technical detail, which is that if we have shape equal to 1, let's insist that stride is equal to 0.
Yeah.
This leaves the layout function unaffected in particular.
Yeah, this does seem to be a one-to-one map to what I've been thinking with this completed layout reflexive generalized inverse conditioning. But yeah, this is really cool.
Awesome. Yeah, and I think it would be a fun exercise, which maybe we can get to later, to like write down a fairly general looking tuple morphism and then try to understand why do these things admit left inverses and right inverses. Because I think you can see from the diagram that it's going to be related to like, including entries which are not projected away, for example, or maybe projecting away entries which are not hit or something like this.
Yeah, precisely. Yeah.
Awesome. So cool. So maybe a point of this is like we have this dictionary. Like if we're working with layouts, they're often tractable. And anytime we have a tractable layout, we can sort of consider it just as one of these tuple morphisms. And if we want to do some algebraic operation, well, instead of doing it at the layout level, we could do it at the level of these morphisms. So again, here, like these compact layouts correspond to permutations as tuple morphisms. And these strided layouts correspond to insertions. So 64 divided by 8 is 8. So that should be an 8. And then these broadcast layouts, right? These correspond to just projections. And so this gives sort of a nice intuitive framework for working with many important layouts. And I guess I wrote this as 128.0, so I should write it like this. Okay, great. So we've seen how we can represent these tractable layouts. And the point of this, as I had mentioned, is we want to understand operations on layouts in terms of operations on the representing morphisms. And so that's our next goal, is to talk about composition, complementation, coalesce, all these different things in the world of these tuple morphisms. And we can develop a nice sort of calculus for working with these things. So let's look at composition, right? We know that if we have an F and G, which are composable, we can compose them to obtain a tuple morphism F followed by G. And our theorem is that this exactly corresponds to layout composition. So here we have encoded layouts encoded by each of these guys. In this case, we have LF is like 4, 6 and 1, 8. And here LG is 4, 2, 6. And let's see, 2 and 1 and 8. And our theorem implies that if you want to know the layout composition of these two layouts, we'll just compose the representing tuple morphisms. And you'll get something like 4, 6 and 2, 8. So great. This is a cool connection between our category and composition. We should mention here that, this doesn't quite do everything we want it to do, because we didn't say that if you start with like a tractable layout A and a tractable layout B, that when you take the representing tuple morphisms, that those things are composable. They might not be composable. And so later on, we're going to show an algorithmic way to sort of take the standard representations and modify them so you can actually compose in this manner. In any case, this is our nice theorem. And in fact, we can phrase this sort of categorically as follows, right? We recall that a functor is some sort of mapping from one category to another. It turns out, omitted this. It turns out that this theorem is really a corollary of the existence of a certain functor. And that's this functor from our category tuple to the category of finite sets. We can define a functor which sends each tuple S to its size as a finite set. And it sends each tuple morphism F to, well, the layout function of the encoded layout. Now, the fact that this thing is a functor is saying that composition of tuple morphisms is composition of the corresponding layouts, right? In particular, if we have an F and we have a G, then this tells us that this composite here, phi LG, should be equal to, so here, this should be equal to and is equal to L F followed by G. So here, if you're not familiar with this, this is something called like a commuting diagram. It's a way to express that certain compositions are equal. But the key point is that it is from this sort of categorical fact that we derive this equality. Okay, great. So now we know how to compose tuple morphisms, and we know that sort of if we have tractable layouts whose representing morphisms are composable, we can compute the layout composition. Let's take a look at some other important operations. And maybe we'll move through this a little quickly. But maybe here's a great example of the power of our theory, where power here means sort of a pedagogical power. Like we can use this to understand what the heck a complement is doing. So here we have a tuple morphism F. This corresponds to the layout LF equals 8, 8. And well, let's see, the prefix product is 2. And this prefix product is 2 times 8 times 2, which should be 32. Well, the claim is that if you want the complement of this F, just map in the entries which aren't hit by F. And that thing is the complement. So here, LF complement is going to be 2, 2. And then this is, well, let's see, prefix product, the stride is 1. Prefix product, the stride is 16. Our theorem is that if you do this very simple construction of just include the entries which aren't hit, the result is exactly the complement of the layout encoded by F. And so this is one way to understand it, right? Earlier, we were discussing this notion of complement, that, oh, it's like somehow like it's the stuff that's not hit. But if you look at like the linearized like layout function, for example, or even one of these 2D grids, it's kind of hard to see that sometimes. Here we see that the complement is what's not hit in a very literal way, right? For this strided 8x8 layout, we see that the complement is exactly consisting of this like 2x2 portion, which is missed in the sense of this sort of tuple morphism calculus that we've developed.
In other words, it's a set theoretic complement.
That's right. It's a set theoretic complement. We're looking at the complement of the image. That corresponds to the complement of the layout.
That's why I call it a complement.
Perfect. Yes, I love when things work out like that. Yes. Okay, great. So again, let's look at another important operation. There's this coalesce operation on layouts. And it was defined in terms of flatten first. Okay, maybe we ignore flatten first. But it was like you can combine adjacent modes when they satisfy some sort of product property. And that property, the reason one would define coalesce in this way is exactly sort of depicted in these diagrams. So here we have a tuple morphism F, right? Let's write down the layout, which is encodes. This is representing the layout. This is representing the layout. Well, its shape is 2, 2, 5, 5. And its stride is 1, 2, 8, and 8 times 5, which is 40. And the claim is that if you want to coalesce this layout LF, all you need to do is take this diagram, which represents it, and collapse adjacent parallel arrows. That's what coalesce is. That corresponds exactly to this operation of like SI times DI equals DI plus 1. So let's write down the answer. In this case here, L coalesce of F is equal to 4, 8, or sorry, 8 rather. And our theorem, right, is that this exactly corresponds to coalesce at the level of layouts.
Sorry, did you mean 425, right? And then you write down the stride.
Yeah, I certainly did not mean to just write down a single tuple, right? That is meaningless. So let's write down the real thing. 425 and 1, 8. And I think we should take a look. Jay, may I ask you, have you seen this message from Mark? I think we want to sort of do some planning on the timing of the remainder of the talk. I'm going to keep maybe inform me on what there.
Maybe we can litigate this in public, because like I think we went through 60 slides. There is like 40 left. I might need to step out at like 2:30. I think we can keep the camera rolling, but like I'm predicting that like
the latter half. So we've done most of the setup already. So
okay.
I think it would actually roll pretty quickly now.
Okay.
Maybe 30 minutes or so. But
okay, yeah, actually that works wonderfully. Okay, let's do that.
Cool. Yeah. So maybe with that in mind, so ending 30 minutes from now is permissible. Is that right? Or 25 minutes? What is the, if you set an end time, I will scale the remainder of the talk appropriately. So.
Yes. I mean, I would say like another 30 minutes would be ideal. I think just so we can plan things out.
So we'll do that. So great. So we've expressed a lot of the key ideas. So let's sort of continue on and see what else we can do with this sort of framework. So great. In fact, this is a natural sort of transition, right? We've sort of told the story of the flat layouts. It's great. We have a one-to-one correspondence between these tractable guys and these two tractable layouts and tuple morphisms. But we don't just care about flat layouts. We care about nested ones too. So let's talk about how we can extend this story to the case of nested layouts. So first of all, let's specify some notation, right? Sometimes I want to write down a nested tuple in a way where I can refer to its entries explicitly and not just write down some random parentheses. So a lot of times I'll write S equals tuple plus profile, right, to represent a nested tuple. So with that being said, we can define our category nest. And again, this is some sort of category whose objects in this case are nested tuples of positive integers, and which lie over exactly the same sort of maps we had in the tuple case. In other words, we're defining a category in the exact same way we define the category tuple. We're just adding a profile to each of the objects. Again, our composition is just going to be functional composition of these maps over which our morphisms lie. So great, we have a precise definition, but what's nice is that we can, instead of dealing with this definition, just draw some pretty pictures. And so let's do that. So here's an example of a nested tuple morphism F. Here I'm writing the F under the right half of the diagram, but really F is referring to this whole thing, right? So the domain of this morphism is, well, it's the flattened version is 2, 3, 2, 3. But this 3 and 2 combining into a 6, this is suggesting, oh, I need to parenthesize these guys together. And then here I'm mapping to 3, 2, 3, 2. And what about this next example? Well, again, the domain here is going to consist of 2 modes, a mode of size 32 and a mode of size 4. And that first mode of size 32 is the tuple 4, 8, and the next mode of size 4 is 2, 2, right? And this maps to the codomain, which happens to be unparenthesized. It could be parenthesized, but most of the time we deal with just unparenthesized codomains. So we'll see later on that this corresponds to a layout which arises in practice. Similarly, we could look at a sort of a much bigger example, right? This guy, which, as is suggested by the subtitle or the title, corresponds to this WGMMA accumulator layout, right? We have a mode of size 128. This corresponds to 128 threads. And then this 32 corresponds to 32 values per thread. And so this isn't all academic, right? We can actually express the layouts we care about using this framework. So maybe I'll leave it to the interested reader to or audience member to write down the layout encoded by this diagram. So again, we can use the same sort of prefix product formula to take one of these nest morphisms in the category nest and write down a layout, which now is going to have some sort of profile. So for example, for this F morphism, okay, we know what the shape is, and then the stride is just computed by prefix products. Let's scroll through a couple more examples. So here's our MMA sync accumulator thread value layout. Again, the shape is determined by the left half of that diagram, and then the stride is determined by taking prefix products. Finally, we have this WGMMA guy. So I don't know if anyone did in this time compute this layout, but what we hope we get is this, this layout of rank 2 consisting of 128 and 30 threads and 32 values per thread. Cool. So let's continue on. The point is that this story we told about flat layouts extends immediately to the nested case, right? We have a notion of tractable layouts generally. They can have nesting. And it turns out that we can prove, right, that the layouts which arise from this category nest are exactly the tractable layouts. Moreover, as we saw last time, right, there's more than one morphism which represents a given layout. But if we restrict to those with a particularly nice form, we can get sort of a canonical representative of each tractable layout. Great. So why do we care about this stuff? Well, it's because these categories very naturally support things like composition and complements and concatenation, etc. Or maybe, well, yeah, we'll see concatenation later. So here's an example, right? We have an F, we have a G, we can compose them by pasting their diagrams. And then our theorem is that, well, the layout encoded by this composition is exactly the composition of the corresponding layouts. So again, there's a categorical version of this, right, which implies the sort of formulaic result. It implies the equality that we just mentioned, which is that we have a realization functor, which takes any nested tuple to the interval corresponding to its size, and it takes one of these morphisms to, not the layout, but rather the layout function of the encoded layout LF. Okay, great. So the story we told about flat layouts extends immediately to the nested case. That's great. Maybe for the sake of time, I'll move rather quickly through these, but the point is just like we defined them before, right? We can coalesce. We coalesce tuple morphisms. We can also coalesce these nested versions too. This corresponds exactly to coalescing the corresponding layout. So here again, maybe just to make it explicit, what is coalescing? It's collapsing adjacent parallel arrows in these diagrams. What is complementation? Well, again, it's set theoretic complementation. So we can have some crazy nested tuple morphism encoding some interesting layout. What is its complement? Well, it's just the inclusion of all of the entries which are not hit. So here's our theorem, right, is that this corresponds to the complement of the encoded layout. Okay, great. Maybe one more that's worth mentioning is concatenation, right? We saw that concatenation was an operation that was very natural for layouts. If you want to concatenate L with L prime, just write down L and write down L prime and put a comma between them and parenthesize. That's it. This is an example of an operation which is like not very naturally supported by these tuple morphisms. And that should not be a surprise. Every length 1 layout is tractable. So if tractable layouts were composed under or closed under concatenation, then all layouts would be tractable. And so it's no surprise that concatenation is sort of hard to do. But in any case, we can do concatenation with these morphisms. The point is that we can concatenate two morphisms if they have the same codomain and their images don't overlap. So that's what we see here, right? This F and G have the same codomain, their images are disjoint, and so we can concatenate them by just allowing them to share the same codomain. And then we usually introduce sort of nesting corresponding to which morphism does that chunk of the domain belong. What's the takeaway? It's just that we have a well-defined notion of concatenation of these morphisms, and it exactly corresponds to concatenation of the encoded layouts. Okay, great. So we should remember, right, why do we care about these concatenation, complement, and composition? Well, one of the reasons is that we wanted to work with logical divide and logical product. And what's great is that now that we've proved compatibility of these composition, complement, concatenation rules with our morphisms, with the corresponding operations on layouts, we can just define logical divide and logical product of these morphisms easily. We just mimic the same definition that's given for layouts. And our theorem is that if you write down the same formulas, you're guaranteed to get exactly the logical division of the encoded layouts of your morphisms. So in other words, if we have F and G and one can form all of these operations, then you can form the logical divide at the morphism level and then take the encoded layout. Similarly for logical product, right? If F and G admit are sort of compatible in the sense that you can form all of these concatenations and complements and compositions, then you can form their logical product as morphisms and then take the encoded layout. So this is in some sense a means by which to compute logical divide or logical product using these diagrams. Okay, great. So this is the final sort of section of the talk. And so we're just going to walk through an example and a cool theorem. The point is this, right? We sort of don't care about these morphisms on their own, right? I mean, maybe I care. I care very much. I think they're very cool. And I think maybe mathematicians might care. But really, we care about the layouts they encode. That's what matters. And so the point is that we want these to somehow allow us to do interesting stuff with layouts. So if we have a tractable layout A and a tractable layout B, we should be able to use our formalism to compute the composition of A and B. So let's see how that works in practice. And this will expose sort of, in particular, why when we compose flat layouts together, sometimes we get like weird nesting. It's going to become very clear in this picture. So let's consider these layouts. We have a 4x6 row major layout and a 12x4 row major layout. Well, we want to compute their composite. So what do? Well, we just write down the representing morphisms. Okay, cool. So we have F and G, we want to compose them. And well, it looks like we're in trouble because what we see is that the codomain of F, this 6,4, is not equal to the domain of G. And so we can't right off the bat compose these things. However, it's possible to get around this algorithmically. And so let's show how that works. The idea is that this pen is not cooperating. The idea is that so we sort of want to factor these compatibly. We want to factor these. We want to modify F and G so that these are composable morphisms, and then we'll compose them, and that will encode the layout composition of A and B. So this is made precise by this notion of mutual refinement from our paper. So maybe I won't give a precise definition, but this is what this looks like, right? The codomain of F was 6,4. The domain of G was 12,4. And we're just going to factor each entry in a way that is compatible. And so that's what we see here. We'll factor 6 into 6, 4 into 2, 2. On the right-hand side, we'll factor 12 into 6-2 and 4 into 2-2. And now we see that these align very nicely. So let's return. So we've modified the codomain of F and the domain of G. And so what we do is we just make a corresponding modification to F and G themselves. So here F went from 4-6 to 6-4. Well, we'll just break up its entries according to this factorization. That's what's shown on the right-hand side of the screen. On the bottom, right, we have this morphism G. We factored the entries in its domain. Well, we'll just make a corresponding factorization of the entire morphism G. In other words, both its domain and codomain. So this is sort of the hand-wavy sort of graphical way to do this. This is made precise using some constructions called push-outs and pullbacks from category theory. In any case, we've modified our morphisms F and G. They still represent the original layouts in the sense that we haven't modified the layout function at all. And so now that these are composable, we simply compose them. The result is this morphism shown on the right. We can compute the encoded layout using our little prefix product formula, and what we get is exactly the composition of A and B. So this allows us to answer the question of, like, why do we get nesting whenever we compose flat layouts? Well, the reason why is because these flat layouts, if you're in the tractable setting, these flat layouts correspond to these morphisms, but like the domain and codomain might not actually match up exactly. So you have to factor some of these modes in order to get compatibility, and then you can actually compose these guys together.
Yeah, there's always an equivalent uncoalesced layout with prime factors sizes.
Great. Yeah, this is a good point, right? You can factor into primes, and this is going to give you the best shot at compatibility of codomain and domain. It's worth noting at this point, right, that here we said, oh, if you find a compatible factorization, this thing might not always exist. There are some nice sufficient conditions. Like, for example, if all your entries are powers of 2, then as long as the size of the domain of G is greater than or equal to the size of the codomain of F, you can always factor these things. For instance, because of what Chris said, right, you can prime factorize, and then you'll just have a bunch of 2s. Those are certainly compatible.
Mm-hmm.
Okay, cool. So I have another example written down. Maybe I'll just sort of skip through this, and whenever we share the slides, the interested audience member can take a look at that. But I just want to emphasize that this sort of computational process we've written down can be formalized into a rigorous algorithm. If we have tractable layouts A and B, we can always compute their composition, if it exists, by the following means. We take the standard representations of A and coalesce of B. We compute a mutual refinement. If one does not exist, then the things are not composable. And there's an explicit algorithm for determining this. This is not a difficult thing. We do a pullback construction. This was our modification of F according to the mutual refinement. We do a push forward construction. This is our modification of G according to the refinement. And then we get composable morphisms F prime and G prime, so we can compose those and take the encoded layout. And so the result is exactly the composite of A with B. Great. So for some closing remarks, right? The first remark is that as sort of came up naturally in the talk, right? This story can, or you can modify this thing appropriately to compute the composition of A with B, so long as A is tractable. Really, for this process to work, B doesn't actually have to be tractable. And maybe we mentioned a little bit about why that is. But maybe for time's sake, we should just proceed to the end of the talk. So let's see what else we have to cover, right? The theorem, I guess, is that this algorithm does what it says it does. If you make these constructions are all well-defined, and it does, in fact, produce the composition of our layouts, if that exists. Maybe we'll just mention a few future directions, right? There's a sort of rich connection of this theory with the theory of operads. You can take a look at our blog post for a discussion of this, especially in the last few paragraphs. In particular, one can define a sort of span category, if you know what that is, which is a sort of very nice and natural formulation of these layout functions, which sort of allows you to compose things directly instead of algorithmically. Some other future directions are, it might be nice to try to characterize the algebraic relations satisfied by these things, right? Algebra is not just about doing a single operation. It's about like taking an expression and simplifying it, right? Distributing multiplication over addition and canceling out multiplication and division. So can one do that with logical product, logical division, etc.? This is an interesting sort of line of thought. A final future direction is we might want to connect this with more general layout abstractions, right? There are lots of things to consider here, right? There are like these F2 linear layouts, there are integer set relations, there are swizzle functions and composed layouts. So it would be interesting to exactly spell out how does the framework that we've developed here connect to these other things.
And I think one thing to say here, as we were saying in the talk, there was a really, we're trying to describe a right action of tractable layouts on layouts. And let's suppose that the layout has values in some Z module. Well, even let's say, for simplicity, some finite field, right, like F2. Then I have a left action by, or even like a F2 vector space or FP vector space. I can then have a left action of the FP multilinear maps along with my right action of the tractable layouts. I think this like covers things like swizzle layouts, for instance. It has a produces a satisfactory theory of such things.
Yes, and you can actually extend the algebra to right actions and abstracted strides as well, and that's what I do in the CuTe paper. So I do that for coordinate strides in the CuTe paper, which is actually pretty straightforward, and I believe maps relatively immediately to these tuple morphisms that you presented here, but you have to be slightly more careful about how you define prefix product. So every time you say prefix product in writing these diagrams or talking about tuple morphisms, you have to be really careful about prefix product. But yeah, I'm curious to see how you guys would approach things like F2 strides, or other mixed radix strides, product groups, stuff like that. There's some really clever stuff that you can play around with strides, with these layout strides, and still define these right actions in composition.
Right.
That go beyond. That go way beyond integer strides. So.
Yeah. Right. Yeah. From the operatic perspective, it's like we're taking this this poset of positive integers under the divisibility relation and doing some operatic constructions. And there's no reason why you are required to start with this particular poset or this particular category or operad, right? You could like feed in something much more general to our sort of formalism, right? And see what comes up the other end. And so maybe this would be a way to think about these various extensions.
Yeah. Okay.
Great. And so as a final comment, or maybe two final comments, there is lots of interesting research going on related to CuTe layouts and layout abstractions more generally. I've listed some important ones here, most notably Chris's CuTe layout representation in algebra, our paper Categorical Foundations for CuTe Layouts, which contain all the details from the talk today, as well as plenty of others, including, for instance, Chris's GPU mode talk, the CuTe documentation, etc. Finally, thank you all for listening. I hope you all gained something from this talk, and I look forward to any discussion which might follow, either here or on the Discord channel.
Thank you so much, Jack. Thank you, Chris. Thank you, Jay. I guess, are you guys like comfortable sharing the slides just so I can post them on the link? Because like I figured like the people might really want to just sort of, at least I want to sort of spend more time like digesting all the core ideas.
Yeah, absolutely. I'll send them to you immediately following the presentation.
Do you want the ones that have been written over by Jack, for instance, or just the
either of both
slides?
The written over one would be interesting, but if you don't have them, that's okay. Up to you.
Sure.
Thank you.
I'll send both if possible.
I guess, Chris, any final questions you'd like to ask?
No, but I'll follow up with Jack and Jay privately. We've had some good conversations before, and I've got some cool things to show them that I'm curious how they approach. So, be good, nice.
Yeah, that sounds
Very
great.
cool.
Yeah, we can talk on the Slack channel, for instance.
Yeah.
Sweet. Well, thank you, folks. We'll talk soon, and thank you so much again, Jack, for this wonderful talk. Really meant a lot, and then thank you for sort of giving us a good tour of all these ideas. It meant a lot. Thank you.
Yeah.
Thank you, Mark. Appreciate it.